The Progressive Power Show at General Motors Technical Center was designed to display and demonstrate the latest results of GM's continuing investigation of various possible forms of automotive power. There are working experimental vehicles using different types of power, such as low-emission conventional engines, electric drives, gas turbines, and steam power plants. In welcoming the nation's press to the show, GM's president, Edward N. Cole, had this to say.
The cars and power systems here today are working experimental models developed by General Motors. They are designed to illustrate current technological progress by General Motors scientists and engineers and by our outside consultants in various fields. We do not claim breakthroughs for any of these projects, and obviously considerable additional development is necessary before any of the vehicles on display could be made available for production. We believe, however, that through constant exploration into all areas of vehicle propulsion, including the actual operation of new systems in automobiles, such as those exhibited today, more meaningful progress can be made.
Reducing air pollution has been a major GM effort for years. Let's review where pollutants come from. While automobiles are one source, they also come from industrial plants, electrical power plants, the heating of homes, and burning rubbish. Narrowing it down to vehicle power plants, pollutants come from exhaust, crankcase, and evaporation. GM research is aimed at reducing emissions in all three areas. Crankcase emissions have been virtually eliminated, and excellent progress is being made in the other two areas. Experimental approaches include modified exhaust manifolds, a very lean fuel-air mixture, the recirculation of exhaust gases, and an intake valve-throttled engine. Still another experimental approach to reducing emissions is the use of a catalytic converter. This specially designed engine incorporates low-emission design features that are being developed for production engines. Several of these experimental systems show promise, and they're being evaluated in extensive testing. Press representatives attending the show have every opportunity to see for themselves. Progress to date in reducing emission has been remarkable. In 1960, a car without any emission control equipment emitted 567 grams of hydrocarbons per day. With the 1970 models in California and the 1971 models nationally, hydrocarbon emissions will be reduced to only 108 grams, or more than 80%. In addition, carbon monoxide emissions are reduced by 63%. Now let's move on to another type of power, electric. The Electrovare 2, developed in 1966, is powered by silver zinc battery packs in its front and rear compartments with modern solid-state electronic controls for an AC electric drive motor. If conventional lead-acid batteries were used, they would weigh more than 2,600 pounds, about the weight of the car itself. These batteries weigh only 680 pounds, but are costly and short-lived. Performance of this electrically powered car is virtually the same as a conventional gasoline-powered small car, except for a limited range of 40 to 80 miles between recharges. The vehicle was used to test new developments in electric power. The Electrovan, also built in 1966 for research purposes, features fuel cells. The vehicle has a top speed of 70 miles per hour, accelerates from 0 to 60 miles per hour in 30 seconds, and can travel about 150 miles non-stop. The fuel cell converts chemical energy resulting from the reaction of hydrogen and oxygen to useful electricity to drive the motor. It differs from the conventional battery in that it operates continuously as long as the liquid hydrogen and oxygen fuels are available. No recharging necessary. However, major breakthroughs are needed to make the system practical. Another power source under experimental development is the zinc air battery seen here in a golf cart. It weighs only a third as much as the conventional lead-acid battery. There is also research in other direct conversion power sources, but efficiencies are extremely low. Electric power shows promise, but at the present time, the power sources necessary to provide reasonable performance and traveling range are far too heavy and bulky. A third major area of power research is steam. This 1969 Chevelle is powered by a Bessler steam engine built under contract to GM Research. A burner heats the water in the boiler, converting it into high-pressure vapor. The vapor expands and drives the engine pistons, then enters a condenser where it becomes water again and is returned to the boiler. This modified Grand Prix, featuring a steam plant developed by General Motors Research Laboratories, is the world's first steam car with complete power accessories, including air conditioning. Newsmen attending the Progress of Power show focused much attention on this car. Problem areas involving steam plants include size and weight. This complete power plant is 450 pounds heavier than the conventional engine it replaced. It required a 7-inch extension of the engine compartment, yet delivers only half the horsepower. Other problems are water consumption, freezing of the water, lubrication, and startup time. The future of steam is uncertain, but this power plant will be an excellent tool for further research. Another external combustion engine, the Stirling engine, has been the subject of extensive research. It is smaller and more efficient, with a variety of potential applications where clean exhaust, quietness, or special heat sources are desired. It differs from the steam plant by using hydrogen or helium as the working fluid in a sealed system. In 1964, a Corvair was modified to use a Stirling engine, with gas circulating through a tank of hot aluminum oxide pellets to provide heat to the engine. The Stirling engine has also been used in a military generator and in experimental marine installations. This test car, Stirlec 2, uses a diesel fuel burner as a heat source for an 8-horsepower Stirling engine. The engine drives an alternator to charge a bank of batteries which provide power to an electric motor that drives the car. The space required for this system, all the engine compartment and trunk space, added weight and high cost, make the design commercially impractical. However, it is a valuable test for continuing research and development. Another combination of power sources is represented in this vehicle. A gasoline engine, or any prime mover, powers a generator which drives electric motors located at each vehicle wheel. On a level road, perhaps only one wheel would be powered. On a steep grade, 2 or 3 or all might be in use. This Delco-Remy electric wheel propulsion system has potential for some military and commercial applications, but cost factors make it non-competitive in passenger car applications for the foreseeable future. General Motors has been studying gas turbine engines and their possible vehicle applications for more than 20 years. The first gas turbine-powered passenger car built in this country, Firebird 1, was introduced in 1954. The latest turbine-powered bus application is GMC's RTX, or Rapid Transit Experimental Bus. The bus is powered by a gas turbine. A regenerator recovers heat energy from exhaust gases before they are released to the atmosphere. A new experimental automatic transmission is also being used on this bus, a toric transmission, which transmits force from one rolling body to another by friction rather than by gearing or fluid. This same type of transmission is being used in the GM steam car. There are no distinct steps or gear changes as in a conventional transmission, just a smooth, continuous progression on acceleration or deceleration. The same gas turbine power plant is used in the Astro 95 truck. It will be commercially available in 1971. However, gas turbines still cannot compete with a conventional internal combustion engine as a passenger car power plant. The high operating temperatures require expensive materials, and fuel efficiency is low in stop-and-go traffic. Other areas of power source research include heat from radioisotopes and nuclear power. Cost, weight, and shielding problems preclude their use in automotive vehicles unless new scientific breakthroughs are made. A continuing research program is to evaluate promising new concepts and developments in any kind of power. In 1956, the XP500 experimental automobile was powered by a free piston engine. It is adaptable to different fuels, but it is noisy and costs are too high to be competitive with conventional vehicle engines. Modification of present piston engines to run on liquefied petroleum gas shows some potential for well-maintained vehicular fleets, although widespread passenger car use may not be feasible. And then there's the Ram Air supercharger system. A smaller engine is used with compressed air delivered to the carburetor for big engine performance during acceleration. The system works well, but costs are high and space limitations restrict air storage capacity. Another continuing stimulus to vehicle research is metropolitan traffic congestion. One approach taken is the development of special purpose vehicles. These vehicles might utilize electric power, small gasoline engines, or a combination of gas and electric power. Some special purpose vehicles under study are relatively low speed performers that wouldn't mix in freeway or boulevard traffic. They would be handy for a run to the supermarket, school, or perhaps the golf club. Another type of special purpose car is designed to transport two people from the suburbs to downtown offices on existing freeways at freeway speeds. The three-wheel design provides excellent stability and maneuverability with either a conventional steering wheel or a simple handlebar. This car is powered by a four-cylinder gasoline engine capable of 80 miles per hour. Still another commuter car, presently in the mock-up state of development, features a combination gasoline-electric power plant with front-wheel drive. While it can carry 2 adults and 2 children, you probably wouldn't use it for a long trip. These vehicles are examples of technical feasibility, one of a kind, examples of the studies continually underway at GM dating back to the early part of the century. In 1900, 4,192 motor vehicles were produced in this country, 1,681 powered by steam, 1,575 by electricity, and only 939 by gasoline engines. Why, starting from such an inferior position, has the gasoline engine achieved the position it holds today? Well, the internal combustion engine has proved to be best suited to the job of powering automobiles. Most of the same disadvantages of steam and electric power that caused them to lose out in the early competition still remain today as significant obstacles to their broad automotive application. A valid reason for supporting the use of electric or steam plants today is their promise of relatively low levels of pollutants. However, if these power plants are ever to achieve broad usage with no reduction in safety, performance, economy, and convenience compared to the internal combustion engine, then major technological breakthroughs will be required. That is why General Motors continues to push research into all types of power sources. However, the present state of technology indicates that clean air quality objectives in the foreseeable future can be achieved most quickly and most economically by further refinement and development of the internal combustion engine, along with improvements in emission control systems and fuels. Meanwhile, Research will continue in all areas of motive power, and the transportation methods of the future may make today's power plants as outmoded as the horse and buggy.